I want to show you some applications of trees, and we'll look at these three applications. The first is sorting efficiently through a list, and the list needs to have some sort of ordering to it. So we'll look at examples with alphabetical ordering, for instance, or numerical ordering. But if you have an ordered list, you can use a tree to search efficiently through it if you're programming some searching algorithm. Then we'll look at evaluating mathematical expressions using a computer. They use a tree to do so. And then finally, encoding characters efficiently in a bit string. We'll talk about those a little bit later. So let's start with what are called binary search trees. And these are what we use to search efficiently through a list. Searching is a big problem in computer science. It's a hard problem to search or to sort things efficiently, and depending on how badly sorted they are, searching can be a hard problem. So a binary search tree is one way of organizing the information and creating a structure that makes it easy to find things and to search through some sort of ordered list. Now, we call them binary search trees because a binary tree is one with a special property. And so we have this definition of a binary tree, and that is that each node has at most two children. So if you go back to some of the earlier examples we saw with trees, you can have a tree that branches off into as many branches as you want at each level, but a binary tree is one that only allows up to two children. So if you look at this example, not every node has two children, but none of them have more than two children. So this one has two children, but this one, for instance, only has one. So with a binary tree, we'll use terminology like the left child and the right child to indicate the two branches that shoot off of a given node. So a binary tree, each node has at most two children. So this is branching idea with left and right branches. So a binary search tree, we can sort a list of items. Again, there has to be some sort of order to them that makes sense for the list we're looking at. So it could be alphabetical or numerical or some other ordering that fits the application. So the idea of this ordering is that for each node in this tree, let's say this one up here, we start at the top node, everything to the left of that node comes before it, and everything to the right comes after it. Now you could switch these around. You could have everything to the right before and to the left after, but just for the sake of consistency and to stick with what seems more intuitive, we'll have things to the left that are less than, things to the right that are greater than, just as we do on our number line, for instance. So let me show you how this works with an example, because it'll make more sense. But before I do, I'll just mention the reason these are so useful is that if you're searching through a list and you have a binary tree like this, what you'll do is you'll compare at each point. If you're searching for a specific value, you'll compare the value you're searching for to the value you find, and that'll tell you whether to go up or down. So for instance, if I'm searching for the number 12 and I hit the number 5, I know I need to go up from there. And if all I'm doing is looking through like a list of numbers like this, if I were to compare 12 to the first number, I would know I need to go up. Then I would compare to the second number, I know I still need to go up, and then keep going. And you notice I need to do 11 comparisons before I find the number 12. But with a binary tree, as soon as I compare it to the first item in the tree, if I know I need to go up, I've eliminated all these possibilities. So I've eliminated roughly half of the possibilities, and I can jump straight to the other half. And then at each stage, you roughly cut away half of the remaining values, so you very quickly can hone in on the correct answer. So that's the value of a binary search tree, is because at each stage you essentially eliminate half of the possibilities and focus down on the thing you're searching for. That's roughly the reason that binary search trees are so valuable and so efficient. All right, so here's an example. We're going to do some alphabetical sorting. Again, there needs to be some sort of way of sorting these things. So we've got some words here that we're going to sort. And so what I'm going to do is I'm just going to start with the very first word. So I've got mathematics, very first word, and that's going to be my root node. Then, to insert the next word, so physics, I compare that to the top level, so I compare that to mathematics. It would come after it in the alphabetical ordering, so I move to the right, and I add a node over here. Then for geography, I again start at the top of the tree, so I compare it to mathematics. It comes before it alphabetically, so I move to the left, and I have geography here. Then zoology, I start at the top. It comes after mathematics, so I move to the right, and I compare to physics. It again should be after that in the list, so I keep going, and I draw another node to the right. So you notice, again, the idea is each node can only have at most 2 children, so when I went to the right of mathematics and there was already something in that position, I had to keep going. So you keep going until you find an available spot to put this word in. Then meteorology, so we'd start at mathematics, and that goes to the right again, so we compare to physics. Meteorology comes before physics, so we move to the left like this. Then geology, again comparing to mathematics, we go to the left. And then we compare to geography, and it would go after that. So we move to the right to geology. Then psychology, starting at mathematics, we go to the right. Then comparing to physics, we again go to the right. And then we get to zoology, and we go to the left, because it comes before that. And then for chemistry, again, starting at mathematics, we go to the left, and then we hit geography, and again go to the left. So at every point, for every node, everything to the left of it comes before that word alphabetically, and everything to the right of it comes after that word. And you can look down this list, and that's true for everything. So say I wanted to search for zoology, I would start up here. I would notice zoology comes after that, so I would jump down to the right, and immediately I would eliminate all of this. So I've eliminated those, I don't need to compare to them. And then I would go to the right again from comparing to physics, and I would find it in 2 steps. Rather than, say, if I wanted to find zoology in the current list, I would have to compare it to each one and just keep going. And if you just had the words listed alphabetically, if I were searching for zoology, you'd have to search through every single item in the list. So binary search trees are very, very efficient because they allow us to eliminate half of the possibilities in one step. All right, I want to show you one more example of sorting a list or creating a binary search tree for numerical values. For this one, you should try pausing the video and see if you can do it yourself and see if you get the same thing that I'll do. I'll tell you that I'll start with 25 as the root node and then draw everything from there. So if you want to pause it and try it yourself and then see what you get, feel free. Otherwise, we're going to start with 25 up here at the top. And then number 17 would go to the left of that because it's before. 19 would also go before 25, but after 17. Then 20 would also go before 25, but after 17 and after 19. 33 would go after 25. 13 would go before 25 and before 17. And then 30 would go after 25, but before 33. Now if you notice, this one here is a little bit less balanced than the previous one. This one here is fairly well balanced, meaning to the left of the first node, there's roughly the same number as the ones to the right. There's 3 of them to the left and 4 of them to the right, which is pretty well balanced. And the more balanced a binary search tree is, the more efficient it's going to be because if there's only, say, one thing over here to the left and everything else to the right, when we make our first comparison, we aren't eliminating half of the possibilities, we're only eliminating one. So the more balanced a tree is, the more efficient it is. Um, and there are ways to balance a binary search tree after you make it, but basically it all boils down to what you choose as your root node as to how balanced it is. We're not going to get into any of that, that's more advanced topics, but if you dig into this more, you'll find that that's one of the issues that you run into that it's interesting to try to solve. So those are binary search trees. They're very simple to make, and they make searching through a list, an ordered list, much more efficient.